this is Calculus 12, Chapter 7.2. We're going to be looking at areas in the plane, and this is areas between curves, areas enclosed by intersecting curves, and integrating with respect to y.
This is important
to understand before moving on to Chapter 7.3, because we need all these tools when we're looking at volumes of revolution. Okay, the area between the curve with an interval is defined as area equals the interval from a to b, absolute value of f of x minus gx integrated with respect to x. Okay, if f of x is greater than or equal to g of x on a to b, then the area is just the integral from a to b of f of x minus g of x dx. And if that's not the case, we must partition wherever f of x minus g of x equals 0, so we're looking for zeros, or we can look at f of x equals g of x, and we're looking for intersections. So, for example, we're not going to do this analytically, we're just going to do this as a concept. So we have f of x, we have g of x, we're given an interval from a to b. The boundaries don't lie on zeros. So here we need to do f of x minus g of x. Here we need to do g of x minus f of x. Swapping, now we need to do f of x minus g of x. And swapping again, f of x, g of x minus f of x. And finally here we have f of x minus g of x. Okay, if the 0 has a multiplicity that's even, then you can treat it as one partition. And area enclosed by intersecting curves, where there's no interval given, this case, we have to solve where f of x minus g of x equals 0. And a will be our smallest 0, and b will be our largest 0. And we have to have two zeros in order to do this, otherwise we do not have an enclosed area. And sorry, let's go back. Here we have 1, 2, 3, 4 zeros. And we have 5 partitions. And this is a general case, not a specific case. And we also have 2 boundaries. Here, it's the same graph. So we still have 4 zeros. Here, g of x is greater than f of x, so we do that. F of x is greater than g of x. And g of x is greater than f of x. And that's it. So our smallest 0 is here. That's A. Our largest 0 is here. That's B. And we have a total of 1, 2, 3 partitions. Again, this is a general case. A specific case, we may have 2 or 1 partitions even if there's 4 zeros, depending on the multiplicity of the zeros. Integrating with respect to y. So some regions are easy to solve by having x as a function of y, such as relations. And we will solve the equations in terms of y and convert the boundaries in terms of y. So here's an example. This is a relation, and this is a function. So we want to solve the equations in terms of y, and we want to convert the boundaries in terms of y. Okay, so we can do a substitution here. Y into here, so x minus 1 into here. X minus 1 squared. equals 2x plus 6. And we have x squared minus 2x plus 1 equals 2x plus 6. And move everything to the left-hand side. We have x squared minus 4x minus 5 equals 0. Factor this, we have x plus 1, x minus 5 equals 0. So we have x equals negative 1, x equals 5. We substitute this into our easier equation, which is this. So we have y equals negative 1 minus 1. So that equals negative 2. Y equals 5 minus 1. So that equals 4. Okay, if we want to look at this on the graph, we have 5, 4. And here we have negative 1, negative 2. And we're going to be integrating with respect to y. So our slices go like this rather than like this. And let's just take a look at that a little closer. If we were to integrate this direction, this is problematic because we have this function subtracting itself. And then we'd have to partition it and have this function subtract the line. So we don't want to set up two integrals unnecessarily. If we integrate in this direction, this is a single integral. Okay, so x left, that's this one. We have y squared minus 6 over 2. All I'm doing is doing algebra on this. And x right, we have y plus 1, and I'm doing algebra on that. And sometimes it's hard to look at it in this direction. We can swap x and y on our calculator and think of that as x. This is y, but we're swapping it on the calculator. This would be xl, this would be xr, and we're integrating this way. And we have negative 2, negative 1, and here we have 4, 5. Okay, anyways, we're integrating from negative 2 to 4. And because xr is bigger, we do xr minus xl dy. And we substitute these ones. And we really don't want to do this as a step. We just want to lead into our actual ones because we don't want to integrate with respect to y and have x's in our functions. So we have y plus 1 minus y squared minus 6 over 2 dy. So we want to just think this step. Okay, and let's simplify this before we integrate. Negative 2 to 4. We want to order this polynomial minus y squared over 2 plus y plus 4 dy. We have plus 1. This is negative 3 and another minus, so that's positive 3 plus 1, that's 4. Integrating this, we have minus y cubed over 6 plus y squared over 2 plus 4y. Integrating from negative 2 to 4. Substitute our values in. Square brackets, minus 64 over 6 plus 16 over 2 plus 16 minus negative, negative. That gives us 8 over 6. Negative, and this is squared, so it's positive. So that's plus 4 over 2. And finally negative, and that's minus 8. And we plug that into our calculator, and we get 18, and our units squared. Since the units aren't specified, we'll just say units. Let's look at another example. Find the area of the region bounded by the curves y equals sine x, y equals cos x equals 0, and x equals pi over 2. Okay, we have our boundaries here, and since the boundaries are here, it makes sense to integrate with respect to x. We'll have cos x minus sine x for this partition, and we have sine x minus cos x for that partition. We need to find this 0, or intersection.
Recall.
And if you recall how to do this from pre-calc 12, we divide both sides by cos. That gives us 1 on that side. We convert this into tangent, and now we have x equals inverse tan of 1. And that is pi over 4. Okay, we already said that cos is larger than sine on the first partition. So we'll formally write this down, cos x greater than or equal to sine x when 0 to pi over 4. And sine x greater than or equal to cos x when pi over 4 to pi over 2. So area equals integral from 0 to pi over 4 cos x minus sine x dx plus integral pi over 4 pi over 2 sine x minus cos x dx. And this is straightforward to integrate. The antiderivative of cos is sine, and the antiderivative of negative sine is positive cos. 0 to pi over 4 plus antiderivative of sine x is negative cos x. Antiderivative of negative cos x is negative sine x. Pi over 4 to pi over 2. Substitute. We get 1 over root 2 plus 1 over root 2 minus sine of 0 is 0, cos of 0 is 1, and negative cos of pi over 2 is 0, and minus sine of pi over 2 is minus 1. And pi over 4, we already calculated that. That's 1 over root 2. That's negative, and another negative 1 over root 2. And simplifying everything, this is negative 2, and these are positive, so we have 4 over root 2, and we have minus 2. We can just divide the denominator. That gives us 2 root 2 minus 2. Okay, and we prefer this over a decimal value of 0.828. This is exact. We want to try to get exact answers when possible. So we know how to do integration. So that's not what we really want to concentrate on. And it's best to look at examples and see how we want to set things up. Okay, in this example, if we try to integrate with respect to x, this is problematic because we have lines that are discontinuous. So it starts, stops, starts again. That means we'll have to partition our integrals. So it's best to integrate in this direction. There's still a partition, but it's far easier. They're partition 1, partition 2, and it doesn't involve, and this one is partition 2. It doesn't involve extra partitioning because we would have to, if we were to integrate with respect to x, we'd have this function subtracting itself, we'd have this function subtracting the other function, and again, this function subtracting another function, this function subtracting itself. So the partitioning is much worse. So we're integrating with respect to y, and we have two partitions. And looking at this one, it's best to integrate with respect to x. So dx, and there's one partition. Here, we're given an interval. If we try to break it up in this direction, again, we'd have more partitions. We'd have to break up this as one partition and this as another partition. This is a partition, this is another partition. So we want to avoid that. And we want to integrate with one partition here, and it's dx, and we have two partitions. And that completes this lesson.